Good morning, Tensor friends. The other day, we looked at how basis vectors can be viewed as derivatives. I'll leave a link in the description. Here is the power of that, the real advantage of looking at it the way they do in differential geometry. Okay, we're familiar with the polar coordinates and their transforms, x into r and theta, y into r and theta, and the opposite, r into x and y, and theta is a function of y and x. Okay, so let's take the partial derivative of r with respect to x, right? So this is x squared plus y squared to the minus to the 1/2. So we take the derivative, we bring down the 1/2, we subtract a minus 2 over 2, we get this. Take derivative of what's inside, 2x. All right, so the 2's cancel, we get x over it. So this is in the denominator. Well, what's x? It's r cosine theta. What's this? Well, that's just r. So r is canceled. So we have the partial of r with respect to x is equal to cosine theta. Now let's do that same thing for y. And by symmetry, you can see it's going to be the sine theta, right? It's the same as this, but sine theta. Now let's do the partial of theta with respect to x. Okay, so here's the equation. You go to an online math calculator because this is hard, and you get this negative y over x squared plus y squared. Well, what's y? R sine theta. What's this? That's just r squared. It cancels one of them, you get this. The same thing for y. You go to an online math calculator, you get this. R cosine theta over r squared. It's just cosine theta over r. Now, what can you do with this? Well, we can use the multivariable chain rule because we're viewing everything as a derivative, okay? So we can say the partial respect to x, so now this is an operator, is the partial r, partial x, the partial with respect to r. The same thing for theta. Now we just found this and we just found that. So now we have an expression for the partial with respect to x as thus. We do the same exact thing for y, and we found this and we found that. So now we have this expression. All right. Now let's change this to the physics, the format that we're used to seeing. And it looks like this. So this is the EX, the basis vector. This is the ER basis vector, and this is the E theta basis vector. So this is the way you see expressions in differential geometry. This is the way you see them in physics. So we do the exact same thing to y, right? So we get EY is equal to this. Okay, what are you going to do with that? Well, you can do this. We always express a position, the vector, in polar, the coordinates as having this x value, this y value, but we plot it on an actual Cartesian plane, right? Well, what if we want to get rid of these? Well, we can, because now we have EY as a function of r and theta and EX as a function of r and theta. So we can just substitute all that in like this. Let's distribute this and this, and we get this. So look, this cancels that. You're just left with this and this. You put them together, you factor out an r. This is the identity 1. So you just got RER. What the heck does that mean? A position operator, a position vector expressed entirely in r and theta is just RER. Well, let's go look at it on a graph. Okay, I'm in Desmos.com. And one of the real limitations of Desmos is you really can't do polar coordinates in Desmos. You have to use the transforms. Everything is in terms of Cartesian the coordinates, okay? So I just define a radius equal to r. It'll automatically draw you a circle. And I defined an angle of pi over 4. So now I can plot a point. So I got a point. And you see I had to use the transpose equations, okay? So there's my point, r comma pi over 4. Now, we know from previous work that the ER basis vector is just the first derivative of the position vector. So that's the cosine theta and sine the theta. So now we can plot that. And look at what's the magnitude of the ER basis vector? It's 1. It's actually a unit vector, right? So if you said, I've got the point a 4 pi over 4, and I want to plot a vector from the origin to that point, well, that's what we just proved, is that all you need for that position vector is to count the number of ER basis vectors in the direction of that point, right? So if we plot R equals 4, that's R, ER, we just count up 4 ERs. So that's what that vector looks like. The theta has no bearing on it because you have specified a point 4 power over 4, 4 comma power over 4. So that is the real power of viewing basis vectors as derivatives. You can do all kinds of fun things like this. All right, see you later.